Hello, good afternoon to everyone. Thank you for attending our joint seminar on integral system and nonlinear mechanics. Today we have Dr. Vladimir Tomov from Lawrence Livermore National Lab, California. He's an applied computational mathematician at the Livermore National Lab. He obtained his PhD from Texas A&M University, College Station in 2015. His research interests are finite element methods, numerical simulation of Lagrangian, arbitrary Lagrangian, Eulerian hydrodynamics, and radiation diffusion and transport, and optimization of higher order meshes. Vladimir is a recipient of several research grants from US Office of Science and US Department of Energy and Lawrence Livermore National Lab. He is also a recipient of several awards, such as Spot Award, Bronze Award, and also the Best Paper Award in American Nuclear Society Annual Meet. And he has also mentored several summer interns at the lab. We thank Vladimir for accepting our invitation to speak in the seminar. Thank you, Vladimir. And it's...
Yes, thank you. Very generous introduction. Happy to be back virtually at Texas A&M. Thank you for the invitation and thank you all for attending. Yes, this talk will be about finite element algorithms, more specifically high order finite element algorithms, and I'll focus on a particular application. I'll show the methods that went into that application. The work I'll present is not only mine. There are this application is rather big now. There are different teams and projects that are contributing. MFEM is our general purpose finite element library here. Marble is the code team, the people that work closely with the code. Ethos is our mesh optimization project, and SEET is a co-design center with the exascale computing program that deals with optimization of high-order finite element methods. Okay, let's go ahead. So the code is called PLAST. It simulates multi-material high-energy density physics with moving methods. Started working on this code as a postdoc. Back then, it was just a research code with 4 or 5 people. And then for the last 10 years, it grew into what they call here a production code that's used to simulate the real things, as you see in the results later. I have some details on the left, but I want to give you just a motivational example why we use the approach we use. So here on the bottom left, this is an explosion test. We at time 0 we deposit a source of internal energy and at the origin, and it gets converted to kinetic, and it detonates. So this is how it goes. So the things to note, to observe here, first, this is a very coarse mesh. And by moving, by doing our Lagrangian method, moving mesh method, we can get a much better resolution. You can see how the mesh, in a sense, follows the motion and gets good resolution at the shock. And one cannot get this level of accuracy with the Eulerian fixed mesh method, especially on this resolution. The other thing is the use of high-order finite elements, including for the mesh. Our mesh is curved, and you can see the level of symmetry we can get in this problem. Again, one cannot achieve such symmetry with a linear mesh on this resolution. And of course, even with material interfaces, the sharpness is even better. And if you want to follow closely the material motion, the fluid motion, then curved meshes are much more accurate in general. So these will be the main talking point in this presentation, the high order finite element methods, the moving curved meshes, and how we deal with those. Okay, quick overview of the ALE approach. First, we have a Lagrangian phase where the mesh moves with the material. The first three pictures are the Lagrangian phase. Then at some point we need to remesh because practical problems, you cannot run Lagrangian all the time. The mesh will collapse, or for example, when materials hit each other, then the mesh between them should disappear in a sense. So for that, one needs remesh, and then when you get a new mesh, we need to move the solution between the two meshes. So in this talk, I will go over these phases and the algorithms that went into each phase, and I will probably go quickly. My goal is to give many algorithms opposed to going into deep detail for one particular thing, and I hope everyone will see something that's familiar and maybe relevant to his work. Okay, let's start with the Lagrangian phase. So it's compressible Euler, moving meshes. It's a staggered discretization. So these are the equations. We have conservation of momentum, mass, total energy, and the mesh moves. Euler equations, there is no physical viscosity. All of the viscosity that comes is artificial to stabilize the system. What we do, we have continuous high order space for the velocity and mesh, L2 discontinuous for the energy, and the mass is evolved pointwise through strong mass conservation, pointwise mass conservation. Here is some example of the high order mesh motion. So yes, this is the discretization. Then some further details, standard finite element, weak forms, we get mass matrices. F here is the force matrix that includes the stress and the artificial viscosity. And at the end, the semi-discrete form is this here. These matrices, everything is evolved explicitly in time. One needs to be careful. With conservation, we have customized RK type methods to make sure momentum and total energy is conserved. Some critical details here. The artificial viscosity is very important. This is one of the options we have. It's the von Neumann type of viscosity is the symmetric gradient of V. Then we have a second order term that is active always, and the first order is only active in compression. Things like these kind of things are very usual for Euler type of simulations. And to get high order, we have things like hyperviscosity, but I don't go into that. The length scale is also very important. The length scale that scales the viscosity terms, we take it in the direction of maximum compression. So here are some results. We can get high order for higher convergence on smooth tests. This is the 3D explosion. We have another one here. This is a more complicated triple point simulation. You can see the shocks forming going through the material. This here is the material interface. I'm only showing only one of the materials. There are other materials around it, but you can see how the Lagrangian motion follows the formation. It requires to get that level of robustness and that level of deformation. It really requires to be very accurate with the length scale and the viscosity. All right, so now at some point when one wants to simulate multiple materials, he will need to simulate mixed cells because we cannot go Lagrangian all the time. At some point, we need to remap, and once you remap, after the first remap, the cell boundaries will not come at the material interface, so you will create mixed zones. To simulate tests like this, for example, these materials must hit each other, so the mesh in between will have to disappear, and that's when the remesh is needed. So there are two main ways to approach mixed zones. Closure models. This is based on evolving volume fractions. It's easy to represent materials, but one can get mixing and diffusion, which may not be good or are usually difficult to handle, or interface reconstruction. So this will be great if it can be done because the interfaces will still sharp, but it's difficult to reconstruct an interface in something like that when you have, so green here is the mixed interface, so you would have to reconstruct a curved interface inside a curved zone. So the approach we took back in around 2015 was the closure models. So yes, the system changes. Now we have K index, the material index, eta K is pointwise volume fractions, sum to 1 at every point. Then there are material masses, the velocity stays. There is one velocity moving all materials, and the energies duplicate. So the closure model, the idea is that one must define how the volume fractions change accurately, and also this heating between materials. The materials heat each other due to the interactions. So this, in principle, it's called closure model because there are no equations for this. People do what they think it's right to get robustness in those mixed zones and to get physical results. And all arguments in this closure business go around this pressure equilibration idea. So what we do, you make an educated guess what the next pressure will be. It's a guess because the system does not evolve pressure, it evolves density, internal energy, and velocity. So the pressure is a derived field, but you can guess what the next pressure will be, and from that guess, you can say what your volume fractions will be so that the pressures go towards equilibration. This is the idea. Some terms are ignored. There are details in this paper, but that's the main idea. The model must define how the materials evolve and how energy and heating is exchanged between materials. Okay, some results. So this problem, for example, without the closure model, it will not work because once the materials hit, here is a fire hits a wall. Once the materials hit, if the heating is not right, what usually happens is you get very big sound speeds which kill the time step, oscillations in the sound speed. But otherwise it works. So these are the different times. And this was like 2 kilometers per second, this fire hitting the wall. And this is, again, more realistic materials, a steel ball hitting aluminum at 3 kilometers per second. All right. Now, ongoing research, we recently started the other approach, I said, the interface reconstruction. Now, the interface is, of course, we are not going to do a geometric, we don't want to do a geometric calculations of a curved interface in curved zones, so we do the good old level set method. So we take a function and its zero level set is the interface, and we move that function. So once you do that, of course, you need to take into account the location of the level set, and we do that with the so-called shifted interface method. The idea is to enforce these interface conditions instead of on the exact location, you enforce it on surrogate mesh faces, gamma 1 and gamma 2 in this case. And you do take into account the distances from your quadrature point on the face to the interface, and do some tricks, Taylor expansions, and so on to get some kind of interaction that you think is physical. So that's the idea. We have a project for that. Here are some results. This is the exact interface. You can see here, for example, we show the distances to the interface from the zones. There are things like marking which zones are mixed, where are the surrogate faces, and so on. But this is one way to do an exact curved interface and represent it in Lagrangian simulation. Some other results. Again, here it's an impact problem. This part hits the wall, and you can see the curved mesh and the curved interface inside. All right, let's move to mesh optimization now. As I showed, we can run Lagrangian for a long time, but at some point you need to do mesh optimization, either because the problem does not allow to run Lagrangian, or you just want to improve the time step. Here an example, we start with this. We do 3,000 Lagrangian steps. We end up at a solution like this. And if we keep running Lagrangian, we reach final time after around 6,000 steps. But if we do a one remesh and remap step, from this we get this. You can see, of course, there is some diffusion because the mesh is not aligned anymore. But then you get to final time, again, a little diffused, but you get it in 1,000 time steps. So it's much faster. It's what people prefer to do. Now, of course, the questions arise: how diffused you are, towards what you want to optimize the mesh, how often do you do it, and things like that. So I'll talk about this mesh optimization business now. First, yes, again, we want to do it only with finite element operations. We don't want to do geometric operations, mostly because of efficiency and generality. The mesh representation, what we do is we store the nodes. In this case, we have a Q2 element with 9 nodes. So we store the positions of these solid bigger dots. And every other position in the mesh is obtained from this expansion with some higher order basis function. So if you change, if you move one node, this whole cell will change. So we optimize the mesh by moving these nodes. Some details how we do this. We have a project called Ethos. It's based on this target matrix optimization paradigm. The idea is that the user defines target elements, like ideal elements. He knows his mesh to look like that. And then from this target, having the reference and the physical elements, we can compute this transformation from target to physical element, and then measure how different they are, and move the nodes to make them similar. That's how the mesh optimization works. So T here is this transformation. Mu is a mesh quality metric. There are many ways to measure differences. I'll show on the next slide, but mu is the metric, and then we try to minimize this integral. Mu is 0 when the target and the physical elements are the same, so perfect mesh, and mu is increases when they're not the same. So minimizing this integral, in a sense, improves the mesh. This thing is nonlinear, so minimizing it, we solve for the derivative equals 0. It's a Newton method. One needs to compute first and second derivatives of mu. That's the main computational difficulty here. Now, a slide about the metrics. The metric, how do you define the difference between the physical element and your ideal element? Well, all metrics use this decomposition of the Jacobian. It can be decomposed into volume part, orientation, skew angles, and aspect ratio. And the different metrics, what they do is they focus on one or two of these, and they are invariant to the other. So, for example, shape metrics, they would only care about skew angles and aspect ratio and be invariant in volume. And then when you do that, you get a better shape from your mesh. It's the main idea. Another thing we can do, in addition to geometric optimization, is adaptivity. We can adapt the mesh to discrete features. For example, here we have a material interface, and we want to adapt the mesh to this interface. What one can do is first choose what to adapt. In this case, we adapt the volume of the elements and the aspect ratio. Well, there is ways. First, one defines a size function, aspect ratio function that tells what these are at every point, then forms this ideal Jacobian, the ideal mesh based on the aspect ratio and size function, and the mesh optimizer takes that and moves the mesh node so that it achieves these ideal targets as much as possible. And this is the example with the impact. Actually, it uses mesh adaptivity in the remesh, so you can see the mesh is the mesh size is optimized to the location of the wall and the flyer, and you can see how the mesh evolves. Other things we can do with the meshes, we can do local optimization. You can pick regions where you don't want to change the mesh or change it less. For example, here I think we preserve exactly preserve this region because the users requested that, while we optimize where things are happening. Yes, lately we've been looking at fitting. So fitting mesh faces to zero level sets that will be used for interfaces. For example, if we have a zero level set function here, so it specifies this circle, and you want to fit the interface between these two materials to that circle to get something like this. The way we do it, again, there is no geometry. It's based on finite element functions. This sigma function here is the zero level set. So what the method does is it marks some nodes. In this case, it marks x2, and it wants to move it to a location where the sigma is zero. This is zero level set. That's what happens in this example, and it's again a nonlinear term, needs derivatives and so on. Some examples for this: simple balls, both for hexes and tets. We can also do it for boundaries. Now, to do it for boundary, to define the zero level set function, one needs a background mesh because the function must be known outside of the domain to have these gradients on both sides. So with that, there is a background mesh. It can be independent of the front mesh. This is the front mesh, and you move the nodes to get a fitting like this. And same idea for interfaces. It's just a combination of some primitives that are used to form a level set on a background mesh, and then the front mesh is fitted to that interface. Okay, so yes, we have many options. These are all high order meshes, but that's the idea. We have methods to optimize the mesh, and maybe some fancier things if the user wants to fit interfaces or adapt size, things like that. So let's move to the remap now. The remap, again, the idea is that we have two meshes, and we want to move the solution from one mesh to the other, ideally without changing it. Of course, there will be some diffusion. The way we do it, we define, again, a PD. It's pseudo-time advection. So U is the mesh velocity, just the difference between the meshes. And the pseudo-time tau goes from 0, 1. And the idea is that the mesh will move slowly to transition like this. And at the same time, we will be solving a PDE for the solution eta. And this PDE will say that basically eta must stay constant during this transition between the meshes. Yes, this is called advection remap requirements. Of course, you want to be conservative. You don't want to change the mass. And you want to preserve local bounds. You don't want to introduce spikes or new extrema. And of course, high order accuracy. You want to be accurate up to some degree on smooth problems. Yes, again, this I keep repeating that, but it's important. It's only finite element operations. We don't have geometrical reconstructions. Now, some details. It's DG. We always do DG. So you can rewrite the weak form like this. This is some upwind flux. So you get this here is total derivative because the mesh moves. That's one way to write it with the matrix inside the derivative. Another way to write it is to take to differentiate in time the matrix and put it on the right-hand side like this. And these are equivalent on fully on continuous level, but on fully discrete in time, they are not, because this one will not preserve constant functions. It will be fully conservative. On the other hand, this one will not be fully conservative, but it will preserve constant functions, and that's actually important for if you want to be able to preserve the bounds. There are details there, but we choose this form because it allows us to preserve bounds. The other thing that allows us to preserve bounds is that we use the high order positive burst time basis. Because if with finite elements, if it's not a positive basis, even though you may be preserving the bounds at the degrees of freedom and the quadrature points, it can still oscillate. But with positive basis, that's not the case. Your function will always be bounded by the values at the degrees of freedom. So now, yes, this is the weak form. There are many details. Then there is this FCT type procedure, Fox corrected transport. What it does is first it defines a low order solution for this, which is diffused but in bounds. Then one can compute the high order, but just solving this will be sharp but not in bounds. And then there is this flux correction. It's called that blends the two so that you get the best from both. You are relatively sharp and you are in bounds. Yes, so we actually have a publicly available mini-app for this called Tremos. It solves both transport and remap, and it's open source, and it has many options how to do this blending and all the solves. All right, now things become more complicated though when one wants to remap the system. Everything I showed up to now was just remapping the scalar. Now we have the system, so we have first we have the volume fractions, the eta, then we have the masses, thermal energies, and what you wanna remap. Well, what the Lagrangian phase evolves are the primal fields. So it evolves density and specific internal energy. Now, the remap phase, the way it's written, to be conservative, one needs to evolve instead of density masses and internal energies instead of specific internal energy. So this is a big challenge. One needs to do first conservation. It comes on the formulation, but the problem is that the bounds preservation must be done for the primal fields, not the conserved fields. So once the volume fractions, for example, are remapped, one must take these ratios and bound the ratio instead of the field that's being remapped, things like that. So this is challenge here, and we spent a lot of time to derive methods that do that properly. They are this paper here. But once that's right, then we can run real things. Again, these are the things I showed, the impacts. This is mostly a toy problem. It's a compression of a ball, but the interface is perturbed, so it develops these instabilities and produces nice pictures. Then this is a more serious test. This is a shaped charge, so it's high explosive here, creates a jet, and this is used for various things. For example, triggering nuclear devices, and cutting armor and things like that. But you see, for this kind of simulation, you need the whole thing. You need closure models. This is a 7-material thing, many mixed zones. You need to adapt the mesh to get the jet properly. You need to have proper remap to remap everything and so on. This simulation uses pretty much everything I showed. Some better videos now. This is the same spherical implosion, but it was taken by some visualization teams here, and they worked hard to make this look good. So pretty much the same, but it's a very high resolution simulation with fancy visualization. Then I have the shape charge, another better visualization in 3D again. Okay, some ongoing research about Remap. Now, one of the requirements when I was talking about the system here is this. When we have the volume fractions, when you remap, you don't want to diffuse the interface. Sharper, if you diffuse material interfaces, that's more mixing, more inaccuracy, and people that run the codes usually don't like that. If you have steel next to something else, you cannot justify too much mixing. So we've been looking at ways to make the profile sharper. So for example, 1D, very simple. This is an indicator function. So 1, the material is present, 0, material is not present. So if you start with this mesh and say you want to remap to this final mesh, ideally you want this profile to stay sharp. Here in 2D, this is the initial profile. See the mesh move. This is a bad diffused result. This is a better, sharper result. Now, one problem is that when you remap, let's say you remap to this mesh and you get this solution, and you look at it, say, okay, it's diffused in 2 zones, it looks okay. Now, when you turn on the walk scale for the same result, so you take this, you just turn on walk scale, and you see this. It's not diffused in 2 zones, actually. It's diffused in many zones. You just don't see it on this plot because you don't have the walk scale. But here you see this diffusion of the small values. And then you look at actually the high order solution without these FCT, focus correction, and so on. And you see that actually the high order solution, which was supposed to be the sharpest thing you can get, it actually creates these oscillations on walk scale. So this was an issue for a long time. Still an issue, but we have some improvement. The question is how to eliminate this diffusion on walk scale and how to keep your materials sharp. And one thing is that maybe you don't care, but if you have special materials like radioactive materials, and even if they leak with such magnitudes, leaking the whole domain, then that's a problem. So people are not happy with that. So the approach we took is we changed the velocity. During remap, there is the mesh velocity, of course, but one can actually detach the material from that and move the material differently. And we define this U star based on the standard velocity that looks at the gradients of your, for example, if this is your volume fraction, this is the diffused region, you can see you can check the direction of the flow, you can check the direction of the gradient, and synchronize this in a way to make this remap sharper. That's the idea. So what happens in the weak form, this is the old weak form. What you do now, you replace the standard velocity with this modified velocity on the right-hand side here, which means that, yeah, I'll move the mesh the same way, but I'll actually not move the material the same way. I will make this nonlinear correction only in the diffused regions. So it is still conservative, but you have this A star here and the modified form, as I said, to have we go from this form where the mass matrix is inside to another form, it becomes like this. So basically, this correction comes down to changing the finite element operator, the advection operator on the right-hand side. Anyway, there are many more details. Just that's the general idea. We do it by changing non-linearly the velocity. That leads to some issues, of course, issues with the time step, issues with the bounce preservation, and all the CFL time step. You cannot just change your velocity any way you like, but we have methods for that. We are writing a paper, and we are getting sharper results. For example, this is the jet of this shaped charge 2D. On the top is the old diffused way of doing it, and this is the corrected solution. All right, and I also wanted to give you an example of adding additional physics. Up to now, all the tests were just multi-material hydro. There were no other physics other than just the shock material shock motion. Now this is radiation diffusion. So radiation diffusion, it means that some materials can emit or absorb radiation, and when they do, they interact with the material temperature, either by heating or cooling it when the radiation field absorbs the. So there is a radiation field that interacts with every material. Higher radiation heats the materials, while they heat at the same time they emit radiation. So so that goes to the radiation field. That's the coupling. So we get this extra equation. It's a diffusion type equation because it's not transport, it's diffusion, and it's gray radiation. What they call it gray means that we take only one frequency. This radiation is like light. It has many frequencies, and when you say, okay, I'm gonna just do one frequency or 1 color, it's called gray. So with that, it's diffusion. We take this HDiff approach mostly because we don't want to deal with DG jumps because the divergence of HDiff, this term goes in L2, so it's all good. It must be treated implicitly because this radiation coupling, this temperature transfer happens on a very short time scale, while the hydro is still explicit. And this is the system. So what we do is we define this nonlinear operator. First, we go with some generic implicit time step, define a nonlinear operator, Newton's method to solve the nonlinear system for these implicit terms, and we end up with a huge Jacobian matrix for this operator that couples all the material energies, radiation energy, and this HDIF radiation flux. So the problem comes down really to inverting this Jacobian matrix. Two approaches. The first approach is to use Schur complements, eliminate equations, and end up with an equation for the HDIF radiation flux, something like this here. And once this is solved, you just back substitute to get the other variables. This, of course, then it goes down to solving the HDIF problem. We have good preconditioners for that, based on hybridization, algebraic hybridization. This approach, though, is not very general. The second approach is to decouple, in a sense, the blocks and perform overlapping iteration by lagging some of the blocks. This is more general when you have when we do multiple radiation groups. Or as I said, what I did above was one radiation group or one color. Now, if you want a better approximation of the radiation energy, you want to take multigroup radiation discretization. Then this block here for the radiation energy becomes full, couples many things, so the backward substitution will not work so well. But with this approach, it all decouples nicely. So with that, and the final thing is, if you want to add the mesh motion, what happens is, if the radiation field is very strong, it can actually move the material around, and on the other hand, the material motion also contributes to the radiation field. Then one needs a Imax time integrator. One needs to be careful how to make it high order, conservative, and all that. We have been working on that. But let's go to some results. So with this, once everything is done, this test here is something that people actually run at the lab on one of the laser facilities. There are 5 materials here. There is some perturbed interface. There is some foam on the inside. And the laser hits this wall. It heats it up. The radiation starts to emit radiation, and it propagates on the inside, forming some instabilities on the bottom. So this is material density. I think this is radiation temperature. If you look closely, you can see that actually the heating goes a little bit in front of the material shock. But anyway, that's the result. And people actually took some pictures of the actual experiment and compared it with the numerical simulation. So the simulation is on top. The true pictures are on the bottom. Looks pretty similar. People were mostly happy with the results. And this is again the visualization team just wanted to make a better visualization of this in 3D. Yes, I'm not even sure how they did that, but they worked hard to make these images. All right, a quick note about the performance. Now, as you know, the new machines are GPU-based machines, and to run efficiently on this, we need different algorithms. The standard finite element assembly, forming a sparse matrix and applying this sparse matrix and storing the sparse matrix is not good, because it's too much memory transfer, too much memory storage, and so on. So what people do for these GPU-based machines is use that finite elements can be a finite element operator can be decomposed like this. So let's say A is applying sparse matrix, finite element matrix. So you can take the different parts. So P is going from the parallel partitioning to your local process. G is going from your local element, from your local mesh to one cell. B then is taking taking the cell, going from the basis functions to quadrature points. For example, evaluation of the basis function on the cell to quadrature points, and D is just action, just computations at quadrature points, and then you go back to get the result. So with this decomposition, one notices that these the first operators PGB, these are pretty much independent of the applications. They are strictly finite element operations, and they're always the same. It's D that is application specific. So with this, one can actually only store the data needed for D and apply this on the fly every time. So this does not need a sparse matrix. The other thing is that for some elements, quotes and hexes, they have tensor structure. So the basis functions, the evaluation of the basis function can be decomposed into 1D basis function evaluations. And for example, then one can apply the mass matrix operator as a sequence of contractions. And when you do that for your whole problem at once, you can actually get big optimization. So for example, if you do this decomposition with some factorization of the basis functions instead of O of P to the D, for the application, for example, of P to the 2D becomes D plus 1. Storage is, again, you only store the D. And assembly, by assembly, we mean computing the entries of D. So these are big optimizations, and that's the general idea. We have a project for that called SEED. It's a co-design centered exascale computing program. And yes, we have worked a long time for that. We usually look at these throughput plots that demonstrate the improvement. So the throughput plot, what it shows is on the y-axis we have the number of process degrees of freedom per second and per parallel unit, GPU or CPU, number of GPUs and CPU, and on the X we have the problem size. So you want to be high, obviously. This tells you how efficiently you are using the machine. So you increase the size, you get more parallel efficiency. At some point, it will level up. That means that taking bigger problem sizes at this point doesn't buy anything because you're not using the machine efficiently. So people run somewhere here a little bit before it starts to level. And we have such algorithms for both the Lagrange and the mesh optimization and the remap phases. The GPU systems, again, much better on these kind of pods. Also increasing the order produces better throughput, better use of the machine because you do more operations locally and less memory transfer. What else? Yes, this is strong scaling. I think this is the mesh optimization phase up to 100 GPUs. But again, we have, I only show some of them. We have such algorithms for all the phases, and that's possible. Again, because we base everything on finite element operations, and this decomposition that I showed here, it's independent of what you actually do. You can always do this as long as you are doing standard finite element approach. All right, sorry. So I went over the different phases of AO with some algorithms or causal models, interfaces for the Lagrangian phase, adaptivity to discrete data, surface fitting, for mesh optimization, the remap. I talked about the advection, synchronization issues, sharpening. Um, Again, we work with MFM. It's our general finite element library. We support that and we try to improve it. It's open source. GeoVis is our visualization tool. If you are interested in the Lagrangian phase, we have a mini app that actually can produce open source mini app that can produce many of the results I showed. Remos is our mini app for Remap. And that's all. Let me finish by saying that we have a summer student program for graduate students at Lawrence Livermore. So if you know students, or if you are a student and think that some of these things are interesting and you can contribute, then you should contact me and we can see if there is something appropriate. But other than that, thank you. That's all I had today. Thank you for
Great
listening.
talk, Vladimir. Thank you so much. Are there any questions for the speaker?
Professor, can I ask one?
Sure, go ahead.
I'm sorry if this question is too trivial. I was wondering, looking from many of the simulations, why were only the quadrilaterals were used? Why not triangles?
Right. We can use triangles, but people in this area prefer quads. One reason is performance. Quadrilaterals have the tensor structure that I mentioned, which means that you can do this some factorization and partial assembly and get these flops. The other reason is that in principle, for the shock hydro, people prefer quads because it's more robust in terms of time stepping. Maybe not so easy to mesh, but once you mesh it, it's the preferable thing to run.
Also, can we mix both of these like in adaptive meshing, where we can have both quads and triangles at the same time? If yes, what happens to the complexity in problem solving?
We can, yeah, because it's finite elements, you can have a mixed mesh, but depends what you want to do. If you want to do these fancy optimizations, performance optimizations, then it's not so good because you have to treat the different cells differently. If you don't care about this though, and you just do standard finite element assembly and sparse matrices, then the finite element operations are independent. It will just work. We can, MFM supports mixed meshes. We can run with that.
And also shape regularity in triangles.
Right, yes.
And you don't have to worry about hanging nodes and losing the structure.
Also, could you please talk about the functional spaces of the test function in the weak formulation?
For which phase in particular?
The functional spaces of the test function that we used in the weak formulation.
Probably in the Lagrangian phase.
Yeah, the first.
The first one. Okay, yeah. So yeah, let's go back. Here we go. Here.
Yes, Professor.
Right. So let's go to the system. So what we do is velocity and mesh are H1 continuous fields. That means that's good because the velocity. Oh, let's talk about the mesh. The mesh first must be continuous. It must be represented as a continuous function. Otherwise, you have like cuts in your mesh. And same for velocity, because the velocity moves the mesh. You really want on the shared faces, you want to have the same velocity from both sides. That's the natural thing to do. You can solve with a L2 this continuous velocity, but then you have to do some averaging, and people do that, but we have found that it's just more convenient to use continuous velocity to move the mesh. So yes, so velocity is h1. Then the energy is L2. It's the standard so-called staggered discretization that people do for finite volumes, but do it for finite elements. So energy is L2. It can have jumps, and the density rho. Density rho, actually, there is no finite element space. It's only evolved at the quadrature points, and you can do this because there is this notion of pointwise mass conservation. It means that the mass of the mass of every cell stays constant. So you can say, for example, that if the mesh compresses, your density goes up. It goes up the same ratio, so that you have the same mass, and you can do this pointwise by tracking the initial and the current Jacobians. So there is no need for a finite element space for density. What was the question exactly about the spaces? Sorry.
Yeah,
Thank you. Yeah, I think you have answered about the shape functions, about the test functions and other things.
Thank you, sir. Thank you so much.
Vladimir, in the next slide, in slide number 5, you had a Q3, Q2 discretization.
Q3, Q2.
No, sorry. I mean, it's in the okay. Let's stop here in the slide number 5. So these Q and Q2 are the artificial viscosity terms, right?
Yes, Q1 and Q2 are just constants that scale.
Yes, some constants. So you need, like, do they have to be certain range in order to preserve the stability? And
yeah, so they are unitless, and their values are 0.5 and 1/4. Okay. And there isn't much theory about this. It's basically ad hoc. People know that this works, and it works good for all cases.
Okay.
The important part is the L, the length scale. Mm-hmm. So this is a linear term, this is a quadratic term. Mm-hmm. The linear term is really the big hammer that diffuses things a lot. And this, when things compress, when the shock comes, this becomes active and it diffuses things. When the shock goes away, we are only left with the second order, and this gives us, because it's second order, it goes down quickly for smooth problems.
So this term is not discretized in the PDE.
Which one?
The mu, the sigma A.
What do you mean not discretized?
No, in the sense, so was it a part of a PDE system, and then?
Right. Yes, this term is not.
Like you typically do the integration by parts and other things.
So this term is not part of the continuous system.
A continuous system, okay.
So it's not physical. It has nothing to do with the Euler equations.
Okay.
It's not like Navier-Stokes where this kind of term is just there in the continuous system, right? Here we put this term. Basically, you can put anything. It's purely artificial. We only put it to get stability. And this term goes into F. It goes in the right hand side. F is so sigma is this thing is like pressure tensor plus this.
So in slide number 12, we see a Q3, Q2 discretization.
12?
Yeah. Any reason why we have Q3, Q2, that higher order discretization?
Because it so for smooth solutions, this can really, if the test was smooth, we can actually get with Q3, Q2, we can get third order convergence.
Okay.
This
so
is
it is not from the stabilization. It is not the reason that the stabilization of the whole big formulation needed such a higher order discretization.
No.
Okay.
We can run any order. We can run
Okay.
Q7, Q8 with the same stabilization.
Okay. Very good.
So the other thing that higher order gives you is more physical mesh motion. This can swirl more, while with the lower orders you get kind of stiffness in the material motion. And this problem actually is a good example because with Q7, Q8 we can really get real vorticity even in the Lagrangian phase. Yeah, didn't put that image here, but can show it on the. If you Google blast code LLNL, you can see what Q7, Q8 does on this problem.